Our new unit is on waves. Here's our different concepts that we'll be going through with waves. The first topic is wave motion. If you drop a pebble in the water, you can see that the ripples from the waves will travel outward from where you dropped the pebble, right? So they tell you that a wave travels along its medium, so it's going to travel along its medium, but the individual particles, so the wave is actually going, let me change colors here. So the wave is actually going these directions away from where you dropped the pebble. So that's the direction, or the wave propagation. But the particles themselves are just moving up and down, up and down. They're not traveling along the wave propagation. Down below we have a wave, and if we take, it's hard to measure distance at a wave. So if we take one point of a wave, and then we follow that wave down until we come up with that same exact point again, they call that lambda, and that's the symbol for lambda, L-A-M-B-D-A, lambda. And it's sort of like an upside down Y. It's measured, since it's a distance, it's measured in meters. Right? So you don't actually have to choose from that specific point. You can choose other points. You could say, okay, let's take a point that's a little bit before the bottom of this wave and go to where it's a little bit of the bottom again. That distance, again, is lambda. Okay, and that's wavelength. So so the high point of the wave is termed a crest, which is the maximum displacement, otherwise known as amplitude. The low point of the wave is known as a trough. All right, so from one point on a wave to another point, that's the wavelength. I guess I should write that, wavelength. And that's measured in meters, and that symbol is lambda. Waves transport energy. That's their function. They transport energy. We have a single wave pulse, or we can have continuous waves starting with vibrations. That's known as simple harmonic motion. We mentioned already that they have an amplitude, which is their maximum displacement, the wavelength, which we know as lambda, and frequency and period we've already discussed. And now we need to talk about wave velocity. We know that velocity is distance over time, right? Meters per second. And we know the distance in a wave is lambda. And the time that it takes to travel one wavelength is known as period. So we get the interesting equation that velocity equals lambda over t. And if we know that frequency is equal to 1 over period, let's go back a little bit. We can take this equation, velocity equals lambda over period, and say that says the same thing as lambda times 1 over the period. And if we know that frequency is equal to 1 over the period, we can put frequency in for 1 over t, and we get this equation, velocity equals lambda f, which is a very important equation. What's the wave speed if the period of a wave is 4 seconds and its wavelength is 1.8 meters? So we use, they want to know wave speed. We substitute in wavelength of 1.8 meters over the period, which is 4 seconds, and we come out with 0.45 meters per second. A fisherman noticed that a float makes 30 oscillations in 15 seconds. So oscillations per time is known as frequency. So the frequency is 30 oscillations over 15 seconds, which was a frequency of 2 hertz. The distance between two consecutive crest is 2 meters. That's lambda. We can solve that. We first solve for frequency by n over t, then plug it in our velocity equals lambda f, and we come out with a velocity of 4 meters per second. What's the wavelength of a wave traveling with a speed of 6 meters per second and a period? So we have velocity equals lambda f, or velocity equals lambda over t. And solving for a wavelength, we can multiply both sides by period. And we get wavelength equals dv. Plugging in our values, 18 meters. The velocity, so our first velocity equation is lambda f. We've already completed that. Our second equation has to do with the velocity depending upon the medium it's traveling through. All right, so that big equation is velocity equals the square root of tension force over the mass per unit length of the string. So the mass per unit length of the string is known as mu. All right, tension force is the tension in the string, and that's a force, and mu is the mass per unit length. So it's how heavy the string is for its length, and that's where mu comes from. So let's take a look at that. What happens to the speed of a wave on a string if the tension of the string is increased by a factor of 9? So we have velocity equals the square root of tension over mu. And now what we're doing, we're increasing the tension by a factor of 9. So velocity, the only thing that's changing is a square root of 9. So since it's in the numerator, it has to be increased by square root of 9. So increased by a factor of 3. What happens to the speed of a wave if the mass per unit of length of the string is increased by a factor 9? So now we have velocity equals tension over linear mass, and the linear mass density is now increasing by a factor of 9. Right? So now we have velocity is the square root 1 over 9, which is equal to the square root of 1 over the square root of 9, which is equal to 1 over 9, square root of 9. So this velocity is decreasing by a factor of 3, square root of 9. So decreasing by a factor of 3. Types of waves. There's two types of waves. There's something known as a transverse wave and a longitudinal wave. Transverse waves, all right, so the motion of particles can either be perpendicular to the wave, that's transverse. So this would be a transverse wave where the particles are moving perpendicular, or longitudinal. Longitudinal is this type of wave here. Where we have compressions and expansion, and compressions and expansion. And how I write longitudinal usually is longitudinal, which means the particles are moving parallel to the direction of the wave motion. The wave is moving this way, the particles are moving that way. Longitudinal, parallel. Whereas transverse, they're moving, and I write transverse this way, and I put a little symbol there to show that the wave and the wave particles are moving perpendicular to one another, transverse. Sound waves are classic longitudinal waves, and you can see this if you go next to a speaker and you see the cardboard and the speaker kind of bouncing. That's actually pumping out those waves. It's areas of compression and expansion. That's what causes sound waves. Longitudinal types of waves are sound waves.